Everyone. So hello everyone, so I'm Robin Rolland, I'm a postdoc at the University of Bremen in Maroon. I'm working with the marine water. And today I'm going to talk about some internal wave interaction that we observe at the seamounts around the general critical latitude. So we'll first show, introduce the study area, show first the time series and spectra, then go back to some theories or what I've understood about the theories, and then try to understand what we see in the data. Okay, so last summer, so we were on a cruise here in this area. So here you have New Zealand, New Caledonia. So we are in the Southwest Pacific. And we targeted this seamount chain here that extends quite far away in the Pacific. So our objective was to study seamounts connectivity, so that's the main part of my puzzle project. But we also deployed two moorings, so north and south, or maybe I should say equatorward and poleward of the general critical latitude. So we have 2-3 weeks lasting mooring, and when I look into the data, I get some interesting things to analyze. So here are the two seamounts. You have the moorings location indicated here. So they are basically on the flanks of the seamounts. So here you have seamount 420. The name of the mooring is LR1. You have the latitude, so I always try to at least put the latitude so you have a reference to understand which mooring it is. So both moorings are located on the flank of the moorings, and this one especially is like on kind of a secondary plateau, so not on the top of the mooring of the seamounts, but on kind of secondary deeper plateau. Here you have mooring schematics that's approximately scaled. So both moorings have upward and downward looking ADCPs. You have the depth range of the measurement here. So I forgot to include the vertical resolution, but it's 10 meters for both downward looking ADCPs, 60 meters here and 8 meters here. There are also some aqueducts, but I will not talk about them for sake of time. So here you have the time series of the velocities at both seamounts. So equatorward of the critical latitude here and poleward here. So what we can learn from here is that there's a clear dominance of internal waves in the measurement. So if you apply a moving average of 2 or 3 days, you see that background currents are on the order of 2 to 4 centimeters where you have up to 20 centimeters per second. And we see also some different vertical scales. So also note that the vertical axis is different on the two panels. We can also look at the shear. So we see more intense shear at seamounts 420, so equatorward of the critical latitude, and we see some kind of temporal modulation with like stronger shear, weaker shear, and then again stronger shear during on the time series. That is less visible, but a bit less visible at the second plane. We can now have a look at the spectra and see what kind of frequencies we have. So on the equatorward mooring, you have a very strong inertial signal that dominates, that is much stronger than the M2 peaks. So I should precise that here it's a rotary spectra, so we are in the southern hemisphere, so internal wave have a counterclockwise polarization. So that's why we have a dominance of the blue curves, and clockwise is the orange curves. And here it's a depth average of the full upward and downward looking ADCP measurements. So the solid line is the downward looking ADCPs, and the dashed lines are the upward looking ADCPs. So we have the dominance of this inertial peak, and We also have a little M2+f peak here and the M4. And if we look at the what I expect for the shear this time, you see that we still have this very strong near-inertial peak, but the M2 peak is very slow, which indicates that the M2 internal tides are low modes. So it's just information to understand what's happening in the data. And it also indicates that the shear that we saw in the time series is mostly inertial shear. So we'll get back to that later. If you look now at the Rotary spectra of the seamounts moorings, so the one poleward of the critical latitude, we'll see way more peaks in the data. So I'll try to summarize. So you have here again the inertial peak, M2 peak that this time is dominant. That's much stronger than at the LR1 mooring. And you see that you have M2+, M2-f peaks. You also have in red and in green the 2 M2+f and 3 M2+f and -f each time also present in the spectra. And you have also M4, M6, and even M8 at the end. And what is interesting here is that M2-f is sub-inertial, so it cannot be the sign of free propagating internal waves. And what's even more surprising is that the peak is on the clockwise component. So it took me some time to find the answer, but I will give you the answer at the end. Why we have these clockwise peaks? It is very strange. And if we look again here at the spectra of the shear, so you have more or less the same information that the M2 internal tides is a low mode. And you still have a quite strong inertial shear, but you also see that the M2+f and M2-f peaks are relatively high compared to the previous mooring. Because now, let's go into a bit of theory of nonlinear wave-wave interaction. So I should say that I started to look at that or to investigate these kind of things 3 months ago, so I'm sorry if I say incorrect things during the presentation, but I try my best to do my homework correctly. So what I've understood is that nonlinear wave-wave interaction are important in the ocean because they basically create an internal wave spectrum. They permit cross-scale energy exchange into the internal wave band. Basically, they can permit the exchange of energy from large-scale waves to smaller scale waves until they finally break and dissipate and create mixing. And among these nonlinear interactions, resonant triad interaction are believed to dominate, and this kind of triad interaction can occur when these two conditions on the frequencies and the wave vector are fulfilled. If you fix omega 0, for example, like M2, you can find some interaction and different interaction. And I can already mention the particular case that is quite well known, the parametric subharmonic instability, where omega 1 equal omega 2, and they are both equal to half the omega 0 frequency. Here you have the latitude dependence of triad interaction that include M2 as omega 0, so from equator, from Olbers and America. So you see that some interaction can occur only in this area. So here you have omega 1 divided by M2 and here latitude. So basically some interaction can only occur until 28.8 degrees of latitude, where different interaction can occur up to 74.5 degrees. So poleward M2 is cannot be a free propagating internal wave anymore. So in the paper, they say that some interactions of the M2 tides favor waves at omega 1 equal f, so the inertial frequency, and M2 - f, where different interaction can favor transfer of energy toward M2+f internal waves. So what I thought is that maybe was the peak that I see in the data can be explained by nonlinear wave interaction. But that's what we will try to see in the data. So Here, just to summarize what we saw in the observation, so we saw that we have a strong inertial peak and M2 peak at both seamounts with the dominance of the inertial peak on the equatorward of the critical latitude moorings. We have this M2+f peak at both seamounts, and we have this curious M2-f peak at LR2 Burton seamount with this strange polarization. So this can for sure be a sudden interaction because we are poleward of the critical latitude, so we'll try to find an explanation for that. So the fourth question I will try to answer here are why F dominates at LR1? Can we have some PSI at LR1 because we are really close to the critical latitude? Are these peaks M2+ and -f generated by triad interaction? And what is the explanation for this peak? So to try to answer the question of why the inertial peak dominates at LR1, I try to compare the wind inputs first between the two moorings. And well, in average, you have more or less, so here you have the inertial wind stress at the two moorings, and in average, there's no such strong difference, which is not very surprising because they are not so far away. But you still have this quite strong event here at LR1 that may explain why we have such a strong inertial peaks at LR1, because it will take some time for the inertial wave to propagate downward, I guess. It's also dependent on what Pascal mentioned this morning. So to test this hypothesis, what I wanted to do is to look at rotary spectra, but with depth, this time not with time, to see if we can see more energy propagation and downward energy propagation compared to upward energy propagation. And if you do that, so here you have the rotary spectra with depth for the downward-looking ADCP and the upward-looking ADCP. What you see is that you don't have, I mean, you have a dominance of, a little dominance of the downward energy propagation, the upward energy propagation, but it's not very terrific, I would say, and especially, so the wind event is at here, approximately, and you don't really see like a burst of, I mean, how can I say, you don't see a strong enhancement of downward energy propagation in the time series following the wind event, and even here you have like kind of a decrease in the upward one. So you would expect that you have first the energy going through the upward and then through the downward ADCP, downward-looking ADCP, but we don't see anything clear here. And if you average over the whole time series, you have a slight dominance of the downward energy propagation, but it's not terrific, I would say. So, in my opinion, it's unlikely that the wind generated explain the stronger inertial peaks at LR1. So, I also wanted to try to look if we can correlate that to the out-peak forcing. It seems like there's some kind of temporal correlation with stronger out-peak tides associated to stronger shear and then weaker, and then again stronger shear and stronger out-peak tides. So I thought that maybe it can be related to some parametric harmonic instability of M2 tides. And what is parametric harmonic instability? So according to this paper, parametric harmonic instability is the decay of large-scale waves. So in our case, it would be M2, and so low-mode M2 waves, into two small-scale waves of approximately half the frequency, so in our case, 2 near-inertial waves. And if I understood correctly again, these two small-scale waves should have more or less the same vertical wavelengths with opposite signs, which means that one is propagating up and the other propagating down. And when we look here at this part of the time series, well, I want to see that there is some upward and downward propagation with opposite direction and more or less similar wavelengths. So to check the wavelengths, I did a rotary spectra of the shear. So here you have the downward shear propagation and upward shear propagation. And so of course I don't have lots of point in vertical, so it's relatively low resolution, but it seems that we have close vertical wavelengths on both the upward and downward propagation. And you see that we have a temporal match of the increase of the propagation of the inertial shear in the time series. So we have waves with two with vertical wavelengths that are similar with opposite sign. We have lower internal tides and we are close to the general critical latitude. So my hypothesis is that these two waves that propagate up and down can be PSI induced near-inertial waves. So usually people try to confirm that PSI observation by computing biocoherence. I don't go into the details, but basically it checks non-linearly coupled wave by looking at phase coherence relating from residential linear interaction between wave triads. So in our case, FF and M2. And so my values are, it's a bit noisy because I don't have a very long time series, but we do have significant values at several depths. So I computed independently for U and V. We have significant values at several depths. So it seems to confirm the PSI generation of, or at least that PSI is happening in the time series. So look at the Richardson number just to see the impact of the waves propagation on the potential enhanced mixing and etc. And we do see a reduction of the Richardson gradient number along the path. It's not really a path because it's time, of course, but along the signal of the near-inertial waves. So highlighting the importance of this kind of event for promoting turbulence in the deep ocean. So to summarize what we saw in this time series, we have a strong inertial peak in the velocity shear and lower M2 internal tides. We have evidence of PSI that probably explains the dominance of the inertial peaks because you have a transfer of energy from the M2 frequency towards inertial frequencies that really explain the strong difference between the two moorings. And we evidence some possible not shear instabilities, but at least we show that the probability of shear instabilities should be increased by the presence of these inertial waves. So quick now on this M2 plus minus F peaks. So it took me some time to find the answer, but actually I found the answer in the relatively old paper from Matthew Alford. So he had just the Rotary spectra again. A reminder. So yeah, it's a paper from Matthew Alford who talks about fine structure contamination. So it's actually a very simple mechanism. So we need to think about near-inertial waves that is if up and down by a low mode internal tide, for example. So you have a nice example of how it looks like in the mooring here. So you have the typical signal of near-inertial wave downward propagation, and you can see the up and down of the signal by the M2 tides. So it's equal that a kinematic coupling, and it's basically just a Doppler shift. And what is interesting with this theory, that is very simple, it's actually a very simple equation. You can predict that the M2 plus minus F peaks have the same amplitude, and that the M2 minus F peak have a clockwise polarization. So that explains very well what I saw on the LR2 moorings. So here you have, I just computed the model of Alford, and in fact you can see that the M2 plus F peak here, and the M2 minus F peak here have the same level, and it's also the same for the 2M2 plus F and 2M2 minus F peaks. So it's really disappointing, but that's how it is. At LR1, so we still have this M2 plus F peak. I'm not sure yet if it's kinematic coupling or if there's some interaction. I still need to dig into that a bit. So okay, let's go for this one. Okay, so that's bringing me to the conclusion. So that's really just a recap of what I just said. So I hope I didn't say too much incorrect things. But I'm happy to take any question or comments, or if you have other ideas to explain this observation, I'm happy to discuss. Yes.